All right, well, I wanted to show you or go over some solutions to a couple of problems. Numbers 6 and 8 are ones that you can already figure out pretty easily. Or not 6 and 8, what was I saying? 30 and 32. They're on pages 6 and 8 of this tablet. But 30 and 32, and then the thing about like 31 and 33 deal with capacitors that are in both parallel and in series, like all together. So anyway, number 30 is much like the one that went over with you yesterday about if they're in parallel or if they're in series. So there's three capacitors. They're connected together. Find the effective capacitance if they're all in parallel or if they're all in series. So if they're all in parallel, uh, oh, that's slow. Hold on. I could probably quit some other programs here. I don't know. This tablet's acting up again today. All right. I quit some other stuff. Okay. So you got three capacitors. If they're in parallel, you draw the circuit like this. So you got one, there's the second one, and then there's the third one. And if they're in parallel, the equivalent resistance is equal to the sum of the reciprocal of the resistances to the -1. So if you go 1 over 5 plus 1 over 4 plus 1 over 9, here I'm just kind of writing it like as a shortcut. Instead of writing all the significant figures and writing microfarad, it turns out that when you do the math, it'll come out to be in microfarad. So a fifth, plus a fourth, plus a ninth, and I predict that it's going to be uh, just slightly less than, or it's going to be less than, whichever of the resistors has the smallest resistance. Hold on, I got to fix that. Enter 1 over 5, 4, 9. Okay, 1.78. Let's see, 5, 4, 9. Hold on. This is the series one. I'm sorry, I'm not even awake yet. That's the math for if they're in series. All right, so 1, 2, 3. All right, so if they're all in series, the equivalent resistance is the reciprocal of the sum of the reciprocals of resistances. That comes out to be 1.78. And if the unit was microfarad for all of them, then this is going to be a microfarad. Whichever the resistance is the least, or capacitance is the least capacitance, the total capacitance is going to be less than whichever the ones has the smallest capacitance. So the smallest capacitance is 4. You predict that the capacitance will be less than 4, and 1.78 is less than 4. So that works out to be okay. In parallel, that's what I drew first. I just didn't want to rewrite the math. I guess it takes just about as long to draw the diagram as it does to rewrite the math. But whenever they're in parallel, the equivalent resistance, so you see REQ, or sometimes you'll see it as R tote, or just as like an R, it doesn't really matter. It's just the sum of the individual resistances. Sometimes it's written as R sub I as like an individual resistance. So here it's just the sum of those oh my goodness. I am not even awake yet. These aren't even resistances, they're capacitances. It's going to be one of those days. I thought that 2021 was supposed to be better. All right. So the sum of the capacitances is just 5 and 4 and 9, and that's 18 uh, microfarad. Boy, that was a tough start for the day. We shouldn't start school until like 9 o'clock or so. All right. So that's it. That's all there is to it. If they're in parallel, it's just the sum of the capacitances, and you should expect a value that's larger than whichever the capacitance is the largest. If they're in series, then you can expect the equivalent capacitance to be less than whichever of the capacitors has the lowest capacitance. So that one's pretty straightforward. That's how that math goes. And then, of course, if you know the voltage, you could calculate the amount of charge on a capacitor by taking the capacitance times the voltage in both cases. Whenever they're in series, the thing that's true is the charge is the same for all capacitors. Whenever they're in parallel, the voltage is the same for all the capacitors. Those are parallel lines over here. These aren't. They're not just parallel lines, but they're equal length lines. This is the battery. It really doesn't make a difference in this circuit. It really doesn't matter at all where the battery goes, it turns out. You could design the circuit so that it's like this, where there's one capacitor over here, and then maybe like the other two are on the other side. And you get this exact same result. It turns out that the position of the battery in the circuit is somewhat irrelevant because the battery provides potential across the two legs of the circuit. We call them legs. This leg here is continuous conduction of electrons through all these individual wires. My tablet slowed down again. And then this other leg of the circuit, the potential is the same everywhere where it's like green on the bottom part. And I don't know, our connection might be... the Wi-Fi thing looks okay. I don't know why that's being slow. So it really doesn't matter where the battery is in the circuit. It's the same design. Sometimes it comes down to just the physical orientation of where the actual like components go on a circuit board, or based upon the physical sizes of the devices, or wherever you have to have a lot of charge delivered, you want to deliver that charge through wires that are as short as possible. So it could be that, like in this design, I would guess that like the highest capacitance capacitor, one that holds the greatest amount of charge, would be closer to the battery, and ones that hold less charge are further away, so that the resistive loss of the electrons as they flow through the circuit is less for the greater number of electrons. Anyway, all right, so number 32. This is a good problem in a couple different ways. It's a blue problem, which should like kind of psych you out. And there's a couple different ways to get to a solution, but I want to show you an algebraic trick that's a good mathematical method in physics that you kind of run into. So the problem says you got two capacitors and they have an equivalent capacitance of 9 picofarad when connected in parallel. So when they're in parallel, you know that the capacitance is just the sum of the individual capacitances. So they could be anything. This is like C1 and this is C2. But what you know is that C1 plus C2 has got to equal 9 picofarad. They could be 1 and 8, they could be 2 and 7, they could be 3 and 6, they could be 4 and 5. They don't have to be integer values, but it turns out that what's nice is that oftentimes they are integer values. That's the way in which electronic components are often manufactured. And then whenever you want, well, so a couple things. If you want a capacitor, if you design a circuit so that the capacitance has to be like 18 microfarad, you just put a 20 microfarad capacitor in place and it's going to do the job. Or if you want a capacitance that's of some non-integer value, you can combine them in series to give you a capacitance that is a like non-integer value at some position in the circuit. But anyway, then there's a second set of capacitors, and they happen to be in series. And when they're in series, the capacitance, or the total capacitance of 9 picofarad is equal to 1 over C1 plus 1 over C2 to the negative 1. So really you've got two equations with two unknowns, which looks like pretty easy to solve. And instead of writing the picofarad, I'm just going to write just the 9. So really you have like C1 plus C2 is equal to 9. And then 9 is also equal to 1 over C1 plus 1 over C2 to the negative 1. And you're like, oh, that's easy. Two equations with two unknowns. There's just this integer of 9 that they're solved for. I'll just like, solve one equation for one of the variables and stick it into the other equation. So if you do it that algebraic method, you can say, well, I'll just make C1 equal to 9 minus C2. And that's pretty simple. And then whenever I see a C1 in this equation, I'll just stick 9 minus C2 in for it. So then you end up with 9 is equal to 1 over 9 minus C2 plus,
Mr. Flynn,
yep.
isn't the one in series equal to 2?
Oh yeah, it's 2. Sorry about that. This is 2, not 9. Let's see. All right. Yeah, cool. Thanks. Sorry about that. But I got a little further. Well, it turns out this is kind of like a failed equation. Anyway, yeah, thanks. So that's 2, 2, 2. You might be like, oh, this is no big deal. This is a hot mess. This algebraic equation is like a complete disaster because you have like sums of reciprocals, and then you have a reciprocal of that, and the denominators are not the same. So if you write this out, it's like 2 is equal to 1 over 9 minus C2 plus 1 over C2. That's garbage. And you could say, well, let's just take the reciprocal of both sides. But then you end up with like 1/2 is equal to 1 over 9 minus C2 plus 1 over C2. And that's still garbage. That's just a hot mess. And you can't just take the reciprocal of everything or anything like that. So what you start with is what seems like an easy algebraic substitution, and it turns into just straight trash. So that method of dealing with finding a solution for a variable in a denominator whenever it's a fractional denominator and the variable is in the denominator, and it's a sum with another variable which is in a denominator, it's it's kind of trashy. It's bad. Getting what C2 is equal Getting what C2 is equal to here is tough. But you might know an algebraic trick, and that's that you can multiply the numerators, or multiply every term by the value of the denominators that appear in each of the terms. In other words, if I multiply every term by 2 times 9 minus C2 times C2, I can end up canceling a whole bunch of stuff out. But that still doesn't end up with a nice common denominator. So let me take a side trip for just a second. And one way to get to an answer here is to just do like guess and check, just kind of be brutal about it, um, which could be pretty quick to do. So if you decide, well, what if they happen to be like 1 and 8? So the capacitances are 1 picofarad, 8 picofarad. That satisfies this because 1 plus 8 just gives you 9. And then over here, if you go 1 over 1 plus 1 over 8 to the negative 1, it'll come out to be some value less than 1. You already know that because whenever the capacitors happen to be in series with each other, the equivalent capacitance is less than whichever the ones has a capacitance of uh, equivalent capacitance is less than whichever the capacitors has the smallest capacitance. So an eighth plus 1 over that. This comes out to be 0.9, and that's not okay. 0.9 is too small. So maybe then you guess it's 2 and 7. So that's 1 over 2 plus 1 over 7 to the negative 1. And hopefully this gets closer to 2. But you still know that it's got to be some value that's less than 2. So you're going to see we're going to drive like closer. 1 over 2 plus 1 over 7. It's 1.6. So we're getting closer. So maybe it's 3 and 6. And it turns out that it happens to be 3 and 6. And you actually get exactly 2, which is nice. So you can do that one with guess and check. But let me show you a mathematical trick. It's a good trick. If you're trying to solve for a variable that's in a denominator, like in this equation, you've got this thing that's 2 is equal to 1 over C1 plus 1 over C2. And you always want to have common denominators in order to find sums of fractions. And how you get a common denominator is by multiplying each of the terms by the product of the denominators. What I mean by that is you multiply each of the terms by C1 times C2. So if you multiply by the product of the denominators, which is equal to C1 times C2. It's actually 1 times C1 times C2 because this is actually 2 over 1, but that 1 is, not kind of really there. So if you multiply every term by C1, C2, you get 2 C1. Well, that's still like a fraction. I got to write it so that it's not a reciprocal. In other words, 1/2 is equal to 1 over C1 plus 1 over C2. And you actually don't need the 2. You can write the 2, but it just ends up to cancel out over here anyway. So just the variables that happen to be in the denominator are equal to C1, C2. So if you multiply every term by C1, C2, you get C1, C2 over 2 is equal to C1, C2 over C1 plus C1, C2 over C2. So if you multiply every term in the equation by the products of the denominators, you end up with this equation, which looks worse at first glance, except that it's not, because here the C1s cancel out and here the C2s cancel out. So you end up with C1, C2 over 2 is equal to C2 plus C1. And now you don't have now you don't have variables in denominators. You just have variables like straight up. And that's where you can now take this expression for what C1 is equal to whenever they're in parallel and make a substitution. So then you end up with 9 minus C2 times C2 over 2 is equal to C2 plus 9 minus C2. I don't like something in the algebra. I guess that's okay. Yeah, it's going to be okay, I guess. So over here, C2 times 9 minus C2 is 9C2 minus C2 squared over 2. And this side's just going to be equal to just 9, because C2 minus C2 ends up to just go away. That doesn't always just go away, but here it happens to just go away. So then it's more like 9C2 minus C2 is equal to 18. And then you can write it as a quadratic. This is C2 squared. As C2 squared minus 9C2, and then it's going to be plus 18. Let's see. C2. Yeah. And then, it's a quadratic. So it's like C2 minus 3 times C2 minus 6 is equal to 0. Is that good? That's good. Yeah, that's good. And the two values 0 then have to be 3 and 6. So you probably or might just decide to, guess and check. And guess and check works okay. You can run into problems on the AP exam and on SATs and stuff where you can guess and check values and try to get closer. If you try 4 and 5, you get a value that's, greater than 2. If this question was something like, instead of them being 2, if it was like 1.8, you might guess like 1 and 0.8 or something like that. Well, it wouldn't be 1 and 0.8, whatever. If this was like 1.8, So like 1 over something plus 1 over something is 1.8. You can end up getting closer to the total value by picking intermediate values that begin to approach the value of 1.8 inside here. But this is a cool method that works pretty universally. And there's a couple places where this will show up later on in the course in optics, because in optics we end up with equations that are sums of reciprocals of values, just like the same as capacitance, but there are kind of different tricks you can do to get to the answer. But the same idea is true. If you're looking to solve for a value that's in a denominator, multiplying numerators by products of denominators is okay. Here, when I say that you can multiply by the product of the denominator, because there's a 2 here as well, you could also be like, oh, I'm going to multiply everything by 2c2. But if you multiply everything by 2c2, what you'll see is you end up with 2c2, oh, c1, c2. I got to fix that. 2c1, c2. So it's like 2c1, c2 over 2 is equal to 2c1, c2 over c1 plus 2c1, c2 over c2. Here the c1s cancel out, here the c2s cancel out, and you just end up with the equation c1, c2 is equal to 2c2 plus 2c1. And that's actually the same equation as this one. It's just that if you take this equation and divide every term by 2, you get this equation anyway. So if you want to be, particular about it, it's not necessary to multiply or to include constants in the numerator, because any constant that you multiply by the numerator will still give you the same ratio of terms in the equation anyway. So I don't know. That's a cool method. I took a whole course in college called Math Methods of Physics, and it was all just about, like, I don't want to say math tricks, not only algebraic tricks, but equivalence tricks and stuff like that to try to get to answers in some kind of way with common mathematical descriptions that are seen a lot in nature. Probably somewhere in algebra 2, you learned to do that, but probably forgot it, or maybe didn't learn it, like, and forgot it right after the test or something. All right. So problem 31 and problem 33 deal with capacitors that are both in parallel and in series. So let me show you a couple examples of how that goes and give you some like background as to the theory behind it. So I'm just going to make up a circuit here. And let's see, I'll put another one, and then I'll have a couple that are in parallel. Okay, so this circuit here, I'm just going to pick some stuff. So this is like 6 volts, and we'll say like 1 microfarad and 7 microfarad. And this is like 3 microfarad and 5 microfarad. It doesn't really make a difference what the values are. In this circuit, there are capacitors that are in parallel and capacitors that are in series. These 2 capacitors over here on the right, these are in parallel with each other. And the way you know that they're in parallel with each other is that there's a junction here where current could flow in one of 2 ways. So the current could flow this way and go to the 5 microfarad, or it could flow this way and go to the 3 microfarad. If the current has 2 different paths that it can take, then those have to be in parallel. If the current must go through any 2 resistors, then they happen to have to be in series. So these 2 here, these have to be in series with each other. There actually isn't current that flows through the circuit, but conceptually, that's the idea, that if electrons were to leave this part of the circuit, they would have to continue to flow through one and through the other in order to get to this junction anyway. So these 2 happen to be in series. I'm going to draw this circuit in a slightly different way, or using the same capacitors but arrange them in a different way to show you another kind of issue. So the thing you want to do is think about in what part of the circuit are you like the furthest away from or the most complex situation relative to the battery. And what I mean by that is every single electron is that leaves the 6-volt battery is going to compel excess charge to gather on this plate. That's a pretty simple thing. And excess charge that's on this plate, so if we have excess charge here, that compels electrons to flow, like in this direction through this little bit of the circuit, and you get negative charge here, and then you get positive charge here. And then there's electrons that are compelled to go in one of two ways. So you end up with negative charge here and positive charge here. So in a way, as electrons are like leaving this battery and heading over to this plate, they're kind of like shoving electrons to the right and kind of down. They're causing electrons to, be compelled to move within the circuit. They don't make a complete circuit, but they're compelled to move. And in a way, like any electrons put on the left plate of the 1 microfarad compels electrons to leave the right plate of the 1 microfarad and go onto the 7 microfarad left plate. And then that compels electrons from the right plate of the 7 microfarad to go in one of two paths. So because it's complex that they can go one of two ways, you want to do the parallel part of the circuit first. So a good way to deal with this mathematically and to be able to back through the circuit is to simplify the circuit. Instead of having a 3 microfarad and 5 microfarad capacitor on the right-hand side of the circuit, you could replace those two with one single capacitor. And what you want to think about is, well, what would the capacitance of that capacitor be? Just calculate what the equivalent resistance of these two capacitors is, which is 1 over 3 plus 1 over 5, and that's like to the negative first. Uh, 1.88. So instead of there being a 3 microfarad and 5 microfarad capacitor on the right-hand side of the circuit, you could have a 1.88 microfarad capacitor there. So I'm going to redraw this diagram as if instead of there being two capacitors over there, there's just a single capacitor. So this is now 1 microfarad, 7 microfarad. Oh, I don't know why I just did that. You guys got to stop me because that's just not right. It's just the sum of those. Just holla. Be like, wait, Flint, that's not right. A 3 and a 5 in parallel is just 8 microfarad. So this is the same as having an 8 microfarad capacitor over here. So now you've got the 1 and the 7 and the 8. And now all of these happen to be in series. And because they're all in series, the equivalent capacitance, that's now 1 over 1 plus 1 over 7 plus 1 over 8. Man, I am not awake today. Uh, 0.79. All right, now here's a thing that you can do, or a thing that's important. Each of these capacitors has a certain amount of charge on them. And it turns out that whenever the capacitors are, I can go one step further, it turns out. Instead of there being just, this is a good thing conceptually, instead of there being 3 capacitors, what if there now were just 1? And if there were just 1 capacitor, it would be 0.79 microfarad. And this is still 6 volts. So here's what I'm trying to tell you. Because the charge on a capacitor is equal to the capacitance times the voltage, if you, I think my battery's going dead. If you know the capacitance and the voltage, you can calculate how much charge happens to be on this capacitor, which is 0.79 microfarad times 6 volt. 0.79 times 6, that's 4.73 microcoulomb. Now, one reason to simplify the circuit in this manner is that once you know what the equivalent charge or the total charge would be on a capacitor that would replace all of these capacitors is that this charge is the charge that exists on each of the capacitors that happen to be in series. Because capacitors in series have the same charge. And because the charge is the same on each of these three, and the charge is 4.73, you can calculate what the voltage is for each of these three capacitors. And I already showed you that in a way. The voltage then is equal to charge divided by capacitance. For this one, if I take 4.73 microcoulomb divided by 1 microfarad, you get 4.73 volts. The micros cancel out. For this one, the voltage is 4.73 microcoulombs divided by 7 microfarad, and that's 0.68 volts. And then for this one, the voltage drop is 8 microfarad, or let's see, 4.73 microcoulomb divided by 8 microfarad. And that's 0.59. And it turns out that this voltage, 4.73 plus 0.68 plus 0.59, ought to come out to be 6. Yeah, it's 6 on the nose. I mean, it could have come out to round to like 5.99 or 6.01 or something like that. Now, why calculating the voltage for each of them is useful is now over here we know everything. You know that for this capacitor, you know its capacitance is 1 microfarad. You know the charge that's on it is 4.73 microcoulomb, and you know the voltage is 4.73 volts. For this capacitor, you know its capacitance. The charge is 4.73 microcoulomb, and the voltage is 0.68 volt. But the part you don't know is what is the voltage drop in the charge for each of the ones in parallel? Well, the rule is that whenever they're in parallel, the voltage is the same. And the voltage across each of these capacitors is whatever the voltage is across the 8 microfarad capacitor. So for the 3 microfarad, you know the capacitance is 3 microfarad, and you know the voltage is 0.59 volts. With the capacitance and the voltage, you can calculate the charge. So if you go 3 microfarad times 0.59 volts, that's 1.77 microcoulomb. And for the 5 microfarad, it's 5 microfarad times the same voltage, 0.59 volts. It's whatever the voltage is for the equivalent capacitor that replaces these two capacitors. 5 times 0.59, 2.95. And then it shouldn't be a surprise that these two these two charges, 2.95 plus 1.77 is equal to well, this one comes out to be 4.72 microcoulomb. And it's only 4.72 because of rounding, but that's the same as the 4.73. So what's true about each of these two capacitors over here is that their voltages are the same, but the charges are different. So for the 3 microfarad, the voltage is 0.59 volts, and the charge is 1.77 microcoulomb. But then for this capacitor, the voltage is the same as it was for this one, 0.59 volts, and the charge is 2.95 microcoulombs. All right, so that's the plan. You can have a circuit as complex as you could ever want, and using the simple rules of how the capacitance works gets you the equivalent capacitances for capacitors in parallel and in series. Just hold on a second. I had a battery go dead. I need. There we go. I can hear again. Headsets need like a battery and they kept cutting out. Okay, so in number 31, that's the same sort of deal. What you want to do is this 4 and the 2, those are in parallel with each other. What you want to do is kind of like draw an equivalent circuit like this. And instead of these two capacitors that are in parallel, those are replaced by an equivalent capacitor that's just a single capacitor. And similarly, this can be simplified even further. We've got the battery and another single capacitor. And depending upon what the problem prompts you to do, you may have to do like an awful lot of work or not much work at all. In this case, when you figure out this equivalent capacitance, you're not done because you're trying to find the charge on each capacitor and the potential difference. That's the same as I just did in this example here. This was a slightly more complex example because there's a second, like a second capacitor in series before the parallel ones, but it's the same sort of deal. You just have one less capacitor to have to handle. And then it's the same with number 33, but I'll just say a thing about 33. It says that there's a 15 volt battery connected across points A and B. So what that means is that there's like a battery in the circuit like this. Or another way to draw that diagram, depends on how you like want to do it or whatever, but there's a capacitor and then it splits off and you have, let's see, you gotta go, one branch has 2, another branch has 1. All right, that's another way to like look at it if you want, where there's a battery. This 20 microfarad capacitor is then in series with 2 parallel capacitors, but one of the parallel capacitors equivalents has 2 that actually are in series with each other as well. So you got to try problems like 31 and 33. Within the textbook itself, there are more example problems of circuits that are complex with combinations of parallel and series capacitors. All of this math and all of these rules will apply the same whenever we do problems that work with resistors. A resistor is a device in a circuit that causes a drop in electrical potential as a result of using electricity. There are devices called resistors that intentionally change voltages in parts of the circuit, but generically, anything that's in a circuit that uses electricity, it could be a battery, it could be a motor, it could be the wire itself, it could be a speaker, anything that ends up, I guess you could say, like using electricity, acts as a capacitor, or not as a capacitor, as a resistor, offers resistance in the circuit. And we draw the diagrams the same way. And the rules are pretty much the same, except they're exactly backward. We're sort of to the point in the course where if you know everything about one thing, the other thing is opposite. In other words, the rules for parallel and series are just switched for capacitors. It's going to be the same thing when we do optics. Like once you learn all the rules for mirrors, the rules are exactly opposite for lenses and vice versa. And then like lenses are either concave or convex. And it turns out that convex mirrors act like concave lenses. So if you do like a double switcheroo, then it becomes the same thing. In other words, like concave mirrors and concave lenses act oppositely, but concave mirrors and convex lenses, they act the same in terms of whether they're convergent or divergent and stuff. So there's a lot of that, like things that are the same but exactly opposite that are sort of coming up. If you can do the stuff with capacitors really well, then the stuff with resistors is exactly the same thing. There's a lot of uh, like repetition and redundancy in a lot of the rules in physics. All right, we're like out of time. Deuces. So try 31 and 32 for tomorrow. Try some other capacitors in different combinations. I'm going to show you some alternative ways to solve 31 and 32. To probably be, I'll try to be more awake tomorrow. What day's tomorrow? Is tomorrow Friday? What day's today? Today's Thursday. Tomorrow's Friday. That's hot. Tomorrow may or may not be our last remote day. They haven't told us either way yet. So I'll either see you Monday in person or see you Monday by Zoom or whatever. But I'll see you tomorrow morning. If you have questions, you can put them in the chat or turn on your mic or whatever. I got to go do some chemistry now.